Hi, and welcome back. We're on our final video for atomic structure, and then we'll end up doing part 2 of atomic structure, which will be the periodic trends. And that's going to be a little bit different. You will have just a few videos for that. So for now, let's move on and see another AP question. Now in this question, we're looking at the average atomic mass of naturally occurring isotopes. Now it gives us the average atomic mass that would go on the periodic table, and it gives us 2 isotopes, and we are asked for the percent abundance. So if we wanted to look at our fraction or our percent abundance, in this case we don't know, so we'll put an X for this one and a Y for this one. And we saw this and you had a homework on it, so I am hoping this is a review. So we take 19.99 times X plus 21.99 times Y, and that equals our average atomic mass. Now, before I forge ahead on this, I think it'd be helpful to estimate what we anticipate it to be. That can often help you in life. Good estimation skills, I think, are very, very valuable. And I'm going to do the rough value of the mass number instead of the exact. 20, 21, 22. And do you notice that what's on the periodic table is way, 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 way down here? Way down here. So you think again of the teeter-totter. The 20th must be weighted more heavily. So I expect X to be actually quite a bit greater than Y. And whether we're talking about fraction or the percent, either way. Okay, so that's a good way to start and a good way to check your mathematics. And so let's forge ahead with the actual algebra of this. Now, I can't have one equation and 2 unknowns, so we need to include a second relationship. The fractional abundance, the sum of all fractions, is equal to 1. Sum of percents is 100. The fractions are 1. Now, there really are a variety of ways to solve this. Since this is so simple, I like to use the elimination. So I'm going to multiply through by 19.99 all the way through so I can maintain my equality. So I'm going to make that 1 and 19.99. Then I'm going to add the 2 equations together, and my X term will cancel, and I will end up with 2Y is equal to 0.19. So my fractional abundance for Y is 0.095. Now I need to convert that fractional abundance to a percent. Back and forth is just by 100, so we're going to multiply by 100. And I get 9.5% for Y. Now to find my percent abundance for X, I can simply take 100 minus the percent. I could take 1 minus the fraction as well. I think it's just easiest to do it as the percent now that we're already here. And I get 90.5%. And so that would be our second answer here. So 90.5. So this isotope is a 90.5% abundant. And this isotope is only 9.5% abundant, just as we predicted earlier. Okay. Now, let's go on to the next one. This next one's going to give you a good idea of why I start with tools of the trade in stoichiometry. I know it seems so random, but as we continue through the year, I think you're going to get that a little bit better here. So let's take a look at part 2. We have a 12.55 gram sample, and we want to go to atoms. So we have a stoichiometry. We need to go from mass to moles. Always go through that whole heart of chemistry, and then moles to atoms. So I'm going to start with 12.55 grams of neon. A few of you aren't labeling your stoichiometries, and I think you're finding yourselves getting lost along the way. So you want to be very careful with that. Now, I want to get to moles, and I like to do these in 2 steps. Otherwise, I tend to flip-flop conversions. 1 mole of neon is 20.18 grams. Of neon. Now, here's where it gets a little tricky, because if you look carefully at the question, it didn't ask me for just neon, it asked me for neon 22. So that means I have to find my neon 22 from this, and our fractional abundance told us that we have 0.095 neon 22, we put that 22 in the upper left, for every 1 neon. Now we can use Avogadro's number, and we want to eliminate moles and go to atoms, and that will be Avogadro's number, so that's 6.02 times 10 to the 23rd per 1 mole. So this we'd done, this we'd done, this was the new addition given a particular isotope. And if we cranked through the math, sometimes forget to do that because I sometimes care more about process than math, but the number is very important. You will lose points. 3.6 times 10 to the 22 atoms within that sample. Remember, that sample's a mixture of both isotopes of the neon 22. So that's the first part of this. And now we're going to be jumping right back into the world of electromagnetic radiation. And this time it gives us frequency and asks us for wavelength. And watch those units there. Now, remember I said write your symbol for that and that. So you're given frequency, you're asked for wavelength. Hopefully your mind jumps right to this formula. In an ideal world, you have that memorized. Memorized, because you can move faster, you can think more quickly, and it bridges gaps in our problem-solving abilities. So you want to really work hard to memorize those things. So if I solve that for lambda, I have the speed of light, since it's nanometers. See how handy it is to know the speed of light in nanometers per second? Not required. If you don't, you have to use the one for meters, and then you have to convert from meters to nanometers. And it's an extra step that I don't think is needed if you'll just memorize a little bit. And if I can memorize it as old as I am, you should be able to memorize it. So that's 690 nanometers, which is visible light. Now we're going to shift gears just a little bit more, and because these questions are fairly integrated. And this time it's talking about a chemical reaction. And we have a molecule that's going to absorb light, and in doing so, it's going to break a bond. And that's how we're going to go from here to here, as it requires breaking bonds. And so the question is, how much energy in joules does it absorb per photon? And we are given the frequency. So we have frequency. We're asked for energy of a photon. Energy of a photon is Planck's constant times the frequency. So my energy will be 6.63 times 10 to the minus 34th joule seconds times the given frequency, 1 times 10 to the 15th seconds to the minus 1. Now, I want you to pay attention. Most people aren't going to write it that way. All right, I write it that way just to try to make some points or get some points across here. And so my energy of my photon was 6.63 times 10 to the minus 19th joules for every photon. Again, a lot of people would just report that as joules, not joules per photon. And then one last thing that I want you to do or be able to do, there will be times you'll see questions like this, and they'll be in the context of a non-calculator situation. So since this is a 1 and that's a 15, I want you to remember that you could do this without a calculator. 6.63 times 1 is obviously 6.63. When we multiply, we add. So minus 34 plus 15 gave us our minus 19 here. So it certainly would have been reasonable to do this mathematics even without a calculator. Now, on to the last part here. Again, this is very much like that last question. It gives us the energy to break that bond as kilojoules per mole. Now this time it asks us, does that photon have enough energy to do it? So we took the photon from the previous problem, and that photon hit my O3, and the question is it enough energy to break it? Well, to calculate that, we have to prove it, and notice it doesn't just say support, it says support your answer with a calculation. And so we have to compare energies. And there's two ways to do that. We could have taken our previous energy in joules per photon and convert it to kilojoules per mole and then compare. All right. Or we really could take the kilojoules per mole and go back to joules per photon and compare. I'm going to start with my previous answer, 6.63 times 10 to the minus 19th. And bear in mind, if you could not do the previous step, you can assume numbers in the following steps. So make use of that when needed. Joules per 1 photon. This is exactly like what we did before. We have 6.02 times 10 to the 23rd photons for every 1 mole. I skipped the 1 photon per bond. Hopefully you've got that. So now we've eliminated photons. Now we just need to go from joules to kilojoules. So the frequency from part I gave us, that frequency gave us an energy that was equal to 399 kilojoules for every mole, or mole to the minus 1, or kilojoules per mole, right? Now, that is greater than my bond energy, so I have to have at least. So that bond energy is a minimum energy, and since I have greater than the minimum energy, then the answer is yes, the bond can be broken. So now that's it for this part of chapter 4. You'll be working on AP questions in class, then we'll have a lab, then you'll take a test, and then we'll move into periodic trends. And until all that, this is signing off.